Last time I gave you an overview of this conjectures, hopefully sufficient motivation for the global well-posedness conjectures. And today I'm going to focus on the one-dimensional problems. And I'll start by reminding you what the one-dimensional conjecture was. 1D global well-posedness conjecture. So this says that if we have a 1D dispersive problem, which is cubic with phase rotation and defocusing, then small HS data implies global dispersive solutions. And here, of course, what S is depends from problem to problem, but what is important in here is that there's no localization imposed on this initial data, so you have an arbitrary HS function. And I'll briefly tell you, first of all, about our first result, the semilinear NLS result, but then I will focus on the quasilinear problem, because we always thought that the quasilinear problems are the harder and the more interesting ones. But let me begin with the semilinear nonlinear Schrödinger, if you want. So take the following equation. With the cubic trilinear form. For the phase rotation symmetry, we need to put here two U's and two U bars. I will always put them in this order. We like to have alternate choices there. The dispersion relation in here is A of xi is equal to xi squared, so it's convex. It doesn't matter if we put a minus sign in here, of course. And then this trilinear form, C, is described by a symbol, C of xi1, xi2, and xi3. Xi1, xi2, and xi3 represent the frequencies of the three inputs. All right, and so now let me write down our theorem here. Oh, maybe I should add to this our initial data, U0. Here, we set things up so that we could work in L2, a very convenient choice. So let's see, let's assume. So we need to make some assumptions about this symbol C of the trilinear form, the alpha C, smaller than C alpha. So this is just a bound on C. This is maybe to say that the problem is semilinear. Then we want to have that conservative assumption that I mentioned the other day. So that would be that C of xi, and derivative with respect to C at xi, and psi. So here we're differentiating in all directions, but we still evaluate this on the diagonal. This we're assuming that they are real, okay? And then C, and this is the defocusing condition. So this is the conservative condition. And the third condition is that C of xi, which by now we know it's real, is greater than some positive constant, which is greater than 0. So this is the defocusing assumption. All right, so this is our assumptions. Then for each initial data u0, such that norm of u0 in L2 is smaller than epsilon, which is much smaller than 1, there exists a unique global solution U such that, and now I want to write down some estimates that are satisfied by the solution. And I'm not going to be super precise here. I'll be more precise for the next problem. But let's say we want the solution U in L6 to be smaller than, there's a parameter in here, a power in here, then we want, I should have put the energy norm first. Let me put it here, L infinity L2 smaller than epsilon. And then I was telling you last time about those bilinear inequalities, bilinear L2 inequalities, UA times UB, A and B are frequency regions in L2 smaller than epsilon squared times VA minus VB to the power 1/2. So here, the image that you should have in mind, you have the Fourier space, you have some region A and some region B, and you're assuming that these two regions are separate, okay? And so for the Schrödinger equation, the group velocity is proportional to the frequency, so this is like the difference between the center frequencies, the power minus 1/2 in here. And also, to be precise, I should say this does not, we're not proving this for all possible sets A and B. We have to be careful. What we're not allowed to do is we're not allowed to make them too small somehow. And if you want to understand what are the scales associated to this problem, you look at this assumption on the symbol C. The symbol C is smooth on the unit scale, and so on the Fourier space, this tells you that somehow the unit frequency scale is the one that matters. And so the easiest way to think of A and B are unit size intervals, but you can make them larger. But you cannot make them smaller than unit size intervals. You can make them smaller, but then yeah, let's just think of them as unit size intervals and larger, with a separation that's maybe at least as large as the size of A or the size of B, something like that. All right. So this is the kind of estimates that we prove for the solutions, and maybe one interesting example in here. What is the simplest symbol C that satisfies all of these assumptions? It's just 1. You take the function 1. So example C is equal to 1. And so now our equation is IUT, IDT plus Laplacian of U is equal to U times U squared, which is the defocusing cubic NLS. And of course, this is a problem where we know we have global well-posedness in L2 and in a large range of Sobolev spaces. So the point that I wanted to make is that even for this problem, the estimates that are given by this theorem are new. And in particular, one estimate that you get in here is that norm of U in L6 is smaller than norm of U0 in L2 with a universal constant. And here we have a small data assumption, but here the small data assumption does not do anything because this problem has scale invariance. So this estimate is actually true for arbitrarily large data. So once you have scaling, then you can go from small to large for free. And it seems a little bit counterintuitive that you prove a result for small data and then you rescale it and get a result for large data. And this, in some sense, is a reflection of the fact that this result is fully nonlinear. Okay. And so one thing that we always like to emphasize when we talk about this results is a couple of key ideas that arise in the proof of these results. And I'm going to put these ideas on one of these boards and leave them there. And then when we go to the next example, we'll walk through the steps and see how each of these ideas comes up in the proof. And maybe there should be more than 5, but we'll stick to 5 because we started with 5 and then we don't want to mess up the numerology. There's a little bit more and I'll mention it as we advance. So one idea here is you want to have good bookkeeping, right? Writing a paper, having a good bookkeeping is absolutely essential. And the tool that we use for bookkeeping is frequency envelopes. And when you talk about frequency envelopes, you have to talk about this in the context of some Fourier decomposition. And one classical way to do this is in the context of Littlewood-Paley decomposition. But in the context of the result that I just told you about, we have a different decomposition. We have a lattice decomposition. In other words, you decompose the Fourier space in unit intervals, okay? And it's quite interesting, and to our knowledge, this is the first time this idea of frequency envelopes was implemented in this lattice situation. So this is for NLS, if you want, and this is for Q and LS, which I'll show you in a moment. So I'll explain more why frequency envelopes do, if you haven't seen this before. Secondly, every time you look at the nonlinear PD and you try to prove a global result, something that has to always be there is your favorite energy estimates. Okay. What will be a little bit unusual compared to the standard approach in dispersive PDs in our energy estimates is that we're not going to care so much about effectively energy estimates themselves, but more important to us will be to write these energy estimates in density flux form. This is an idea that has been around for a long time. I don't even know where it comes from. Third idea, and this is something which together with Mihaela we have been playing with for many years now, is given a problem, you might think of some energies and see how they behave in time. But it usually becomes very important to custom build your energies so that they have a better conservation. So I'll tell you about modified energies. These are also in density flux form. Maybe the next key point here is to study interaction of waves. And the interaction of waves, we study it using interaction Morawetz inequalities. Not exactly the classical version of interaction Morawetz, enhanced version of interaction Morawetz. By the end of the entire story, perhaps you won't even recognize the original interaction Morawetz in those. And all of this, both the modified energies and the interaction Morawetz inequalities, happen somehow using these formulations with multilinear forms, so nothing is localized. Everything, all the operators are non-local, but we keep the name interaction Morawetz inequalities. And finally, something that I mentioned before, Strickard's estimates. And that's an entire story unto itself. Maybe I should give some pointers here. The idea of frequency envelopes, this comes from Terry Tao, maybe around 2000 or so. I remember when I first saw it, I saw, oh, this is a cool trick. I should be using it. And energy estimates, well, everybody does it. Modified energies, maybe about 10 years ago, we're looking at, also with Mihaela, and at the time also with John Hunter, we're looking at how to implement normal form methods for quasilinear problems. One key difficulty when you have a quasilinear problem is that your usual normal form transformations turn out to be unbounded, and you need to have some way to address that, and our solution to that was what we call the modified energy method, where instead of trying to change the unknown, the solution, you change instead the way you measure it, you change the energies, and you make your energies better preserved rather than make your function satisfy, let's say, a cubic equation. Interaction Morawetz inequalities, this go back to the I team. That's about 20 years ago, if I remember correctly. But we are interested here in low dimension, especially dimension 1 and dimension 2, and the original formulation of the interaction Morawetz didn't quite work in dimension 1. And in dimension 2, maybe I'll say a word why later. And instead, there was another version of the interaction Morawetz due to Planchon and Vega that we found it to be closer to what we needed. All right, and so Strickard's estimates, like I said, is a story into itself, and I will spend the last lecture of the cycle talking only about the Strickard's estimates in several contexts. Okay, so now let's go to the problem that I want to tell you about today. There's, in effect, if you want, two problems. The first problem, let's call it QNLS, quasilinear Schrödinger equation, IDT plus G of U dx2 applied to U is equal to some nonlinearity which depends on U and derivative of U. So here we have a metric that depends on the unknown function. And if you want to make the problem a little bit more complicated, you can also look at dq and ls, where you do the same, but now you allow the metric to depend both on the solution and its derivatives. here you might say there's no change from this line to this line concerning the nonlinearity, but in this nonlinearity, in order to have a good scaling, you want to assume that here you're at most quadratic in the derivative of u. All right, and there's a very close connection between these two problems. Essentially, if you take a solution to this second problem and you differentiate it, you get a solution to the first problem. So everything, I'll tell you about this problem, but everything carries over to the second problem, one derivative higher. Okay, very simple. All right, so now let's see. I want to say what kind of assumptions we put in here. Let me talk about the first one. So we want to say that the problem is cubic, and that has two parts. G has to be quadratic, at least quadratic. And then this nonlinearity n to be at least cubic. Then we want to have the phase rotation symmetry. So in particular, G should be invariant with respect to phase rotation. So G should have a U and a U bar in it if you want. And this N should have two U's and one U bar at the leading order. And finally, to talk about the remaining assumptions, we take this quasi-linear problem and close our eyes a bit and think of it as a semi-linear problem. In other words, take an expansion of the equation with respect to homogeneity of the expressions that you see in here. And then we write the equation in the following form: I dt plus dx2 applied to u. So this would be the linear part. And on the right, I put everything that's nonlinear, and I'll have terms of order 3, terms of order 5, and so on and so forth. Because of the phase rotation symmetry, all the terms that I put on the right will have odd order. All right? And so the first term in here would be u bar, and u. All right? And then plus higher order terms. But here high order means high order in terms of homogeneity, right? Terms of order 5 and so on. And now we look at this symbol C, and the first thing we try to understand what is the size of it. And so here we have two derivatives, okay? And here we have at most quadratic in this expression in here. So overall, C has two derivatives in it, right? And so if I'm looking at C of psi, psi, and psi, the trace of C on the diagonal, this would be a priori smaller than 1 plus psi square, right? Psi square stands for the two derivatives, and we could also have terms without derivatives in here potentially. So what I want to write down now is what does it mean for the problem to be defocusing. And that would be C of psi, psi, and psi greater than 1 plus psi square. So this guy is real and has size at least of the order of 1 plus psi square. So just if you want an example, I can write down one in here. So it would be I dt plus, let's say, 1 plus, let's see, plus or minus 1 minus, no, it's plus u square dx square u would be u times u square. So this would be an example of a quasi-linear defocusing problem. So I made sure I put the right sign in here, and I made sure I put the right sign in here. So this guy in here gives us the c-square contribution. This guy in here gives us the 1 contribution. All right? If you change either of these signs, then the problem is no longer defocusing. And of course, you can add more terms, but that's enough. All right. And so maybe the last thing that I wanted to mention about this problem, in particular QNLS, this has what we call dimensionless scaling. So you look at u of t and x goes into u of lambda square t lambda x. This is the scaling of the problem. The critical Sobolev norm is h1/2, because that's what corresponds to L infinity. So S critical is 1/2. So your ideal target for local solvability for global results possibly is getting as close as possible to h1/2. All right. So maybe before I begin stating some results, I can give you a quick history about this problem. And maybe even before looking at quasi-linear QNLS problems, people looked at a simplified problem, DNLS, which would be I dt plus dx square u is the nonlinearity, depends on u and du. All right, so that's simpler, but many of the difficulties are already present in this problem because of the infinite speed of propagation that's associated to the Schrödinger equation. And one sort of fundamental step toward understanding this problem came from Mihaela, who looked at an even simpler problem, changed the nonlinearity to just an arbitrary first order term. And what Mihaela observed is that if you want this problem to be solvable, then you need to impose some integrability condition on this gradient potential B. So naively you might say you need B in L1, but in effect it's enough that the integral of B, the antiderivative of B stays bounded. And this is perhaps not the most interesting in one dimension, but the same is true in higher dimensions, and that's where really the thrust of Mihaela's work was, in higher dimensional problems. And then there were a number of people, and then so this was one important idea, and the other next important idea that came was the idea of local smoothing. Which I like to call better local energy decay. So this was work, independent work of Scholin, Constantin and So, and Vega, that happened in the late 80s perhaps. And then for problems with variable coefficients, there was also work of Doi, which played a role. And so that eventually led to, let's say, DNLS local well-posedness. And there were a couple of contributions in here. First, Koenig, Ponce, and Vega had a result for reasonably smooth and localized data. And then the question came about, just as in my talk perhaps, can one do local well-posedness in Sobolev spaces? That's when you run into the Mizuhata obstruction, and if you think about it for a moment, you immediately realize that in order to ensure that, so this B in here, if n is quadratic, B is like Q. An L2 function is not in L1, fact of life. And so that doesn't quite work for quadratic problems. But if you make your problem cubic, then the square of an L2 function is in L1. So you can hope to get L1 in here. And that's why if you want to work in Sobolev spaces, it's not a bad idea to work with the cubic problems. And so there are a couple of papers, and maybe I'm not getting them all, but let me write them down. So Board, Hayashi, Naumkin, and so, and then Colin, and then Poppenberg, and then Lin and Ponce. Actually, I got them wrong. Sorry. Let me read from the wrong line. It happens. So I should have put here Hayashi and Ozawa and Kihara. All right. And then when we go to QNLS, there's a similar story, which starts with Kenny, Ponce, Vega, and then, so this is for localized data, and then the other papers for HS data at higher regularity. And maybe the more recent result for QNLS was the result that I got together with Marzola and Metcalf. That was a little bit more than 10 years ago. And our result says that you have local well-posedness when S is greater than 2 for this problem. So that was our attempt at the time at the low regularity local well-posedness result. Low, maybe you take it with a grain of salt, because you see that it's still 3 derivatives above scaling, but that was the best we could do with the technology that we could come up with at the time. All right. So another thing I was telling you last time is that to our surprise, we realized that our technology for the global result also gives better local well-posedness results. So let me start with that. So this is local well-posedness. This is with Mihaela in 23. So here we are simply assuming that the problem is cubic, okay? Is locally well-posed for S greater than 1. And so that's an improvement of 1 unit after over my previous result with Jeremy and Jason. And I also want to make the argument that this result is almost sharp. Almost sharp, maybe except for the endpoint S is equal to 1. which we did not do, and hopefully somebody will either do it or disprove it in the future. Why do we think this result is essentially sharp? Well, I was telling you about how you get from this equation to this equation by differentiating once. Now, what happens if you differentiate this equation one more time? And then you get the equation for du, right? Then you have these derivatives hanging around. And let's imagine that you're very generous and you put derivatives where you like them best. And you try to make the problem as simple as possible. So this is a heuristic. Then if U solves Q NLS, then du solves something like NLS 3, right? The cubic NLS. And now imagine that you take the cubic NLS, which we have up there on the board, and we sneak an I in front of U times U square, in front of the nonlinearity. That would generate the blow up in L2 in finite time, would also generate ill-posedness below L2. Okay, and so that's our heuristic as to why this S is equal to 1 should be a sharp result. Now, this is a quasi-linear problem, and when we talk about well-posedness for quasi-linear problems, we rely on Hadamard's notion of well-posedness, so we ask for existence, uniqueness, continuous dependence. So we actually got curious and went and read Hadamard's paper from nearly 200 years ago in a language very different from the way we write the math nowadays. And so everything is put in words, sort of without formulas. But you can see that he had the idea. But in addition to these three properties, we add maybe two more properties. One, call it higher regularity, which is that if in addition your initial data has more regularity, then that regularity is preserved, and a weak Lipschitz property. So the data to flow, the data to solution map, the flow map, because the problem in quasi-linear is only continuous, but it is Lipschitz in a weaker topology. And the weaker topology that we use is simply the L2 topology. We didn't worry about making this the most general. L2 works, so we were happy with it. All right. So this theorem also gives Strickard's and bilinear L2 bounds for the solutions, and I'll write them down in a moment. Maybe the next thing I wanted to show you is the global well-posedness result. So also in the same paper, with Mihaela. So this says that, let's say, cubic. So here we put all of these assumptions. And so that I don't copy them all, let me just say cubic defocusing. That's the important thing. Q and LS is globally well-posed in HS for S greater than 1. So in some sense you could say, well, really we should state only one theorem, right? Because this is local well-posedness and this is global well-posedness for exactly the same kind of initial data. However, the proofs of these two results are different, and you cannot talk about global well-posedness in a function space before you have local well-posedness in the same function space. Whereas we hope that we conjecture that the local well-posedness result also works for large data, of course this will in principle be a much difficult proposition and perhaps impossible for large data. All right. And for now, I'm avoiding writing down estimates. This is also, by the way, a quasi-linear result. And there's one difference, major difference, if you want, between the local result and the global result. In the local result, we have estimates for differences of solutions. Okay, in a weaker topology, but we do have estimates for differences. But in the global result, we do not have any estimates for differences of solutions, zilch. Okay, and so that reflects the fact that the proofs of these two things are different. Yes.
The second theorem, so is small data, the global well-posedness.
First, everything is small data. Where is it? I should small data. Right. Everything I've been talking about is small data. The only exception is that problem where we had the scale invariance. Okay. And so I want to then go back to our list of key ideas and work our way through them. Before I do that, I want to give you some idea about what are the resonant interactions in this problem, and at the same time set up some notations. Like in any nonlinear equation, when you study global, even local well-posedness, nonlinear interactions, resonant interactions are the enemy. So you have three frequencies, psi1, psi2, and psi3, which interact. The output will be at frequency psi1 minus psi2 plus psi3, minus because of the complex conjugate. Okay, we call this guy psi4, and then we write this relation in a symmetric way. Delta for xi is equal to 0. Okay, so this is the sort of signed sum of xi's is equal to 0. This tells you what happens with the spatial frequencies, and then we look at the time frequencies. Here our dispersion relation is xi squared, but let me use the letter omega for the dispersion relation. So omega of xi1, omega of xi2, omega of xi3. These are the three input frequencies. The middle one is complex conjugate. So we get at the output omega of psi1 minus omega of psi2 plus omega of psi3 as the output frequency. And the interaction would be resonant if this guy is omega of psi4. All right, where psi4 is the output frequency. So we write this as delta 4 omega of psi is equal to 0. So to understand what are the resonant interactions, you have a system with two equations and four unknowns, which in principle gives you a two-dimensional set of solutions. You can do the algebra easily, and the set of solutions is the set of pairs for which psi1, psi3 is equal to psi2, psi4 in any order. Okay? So these are the resonant interactions for in particular for the cubic NLS if you want, but also for the quasilinear NLS, because we're only looking at the corresponding linear problem. We call this the resonance set, okay, calligraphic R. But I was also telling you last time that really the worst case scenario is when you have parallel interactions. Well, if these frequencies are not equal, then we have transversal interactions in here. That's better. So the worst case scenario is when all frequencies are actually equal. And that's what we call R2. Psi1 is equal to Psi2 is equal to Psi3 is equal to Psi4. We refer to this as the doubly resonant set. Okay, and this is our real enemy. We try to defeat this set. We don't like this set. We want to do away with it, and we'll see what happens. All right. So let me start with the first item now on our list, frequency envelopes. And let's see how we use these frequency envelopes to formulate our setup of the problem. So, in essence, what we want to do is we want to start with a Littlewood-Paley decomposition. All right, in dyadic shells. And then we want to measure how much of the solution U is in each of these shells. And of course, you might say, at the level of the initial data, for instance, you might want to look at U0 lambda in L2, right? And if you have a linear constant coefficient flow, then these quantities will propagate well in time. But if we have a nonlinear problem, then these quantities will no longer propagate well in time because you will have cross interaction, right? And so Tao's idea was, well, perhaps instead of looking at the size of these guys, I should put sort of an umbrella on top of this and choose this constant C lambda so that they don't vary a lot. So you ask that C lambdas be slowly varying. And slowly varying means maybe C lambda over C mu smaller than lambda over mu to the power delta, small power in here, and greater than mu over lambda to the same power delta for mu less than lambda. Okay, so the fact that they don't vary too much gives you a chance to still use this envelope in order to estimate cross interactions between different frequencies. All right? So this is what we want to do for our problem, except we change the notations a little bit in the sense that we are in HS, and we'd like not to worry about the powers of lambda being contained in C lambda. So we put here lambda to the power minus S to capture the HS regularity. And then we also want our initial data to be small, let's say of size epsilon. And so we put an epsilon in front in here. And so in this way, we put our initial data under an HS envelope. And if we do this, then we have ensured that the norm of C lambda in L2 is smaller than 1, which corresponds to a norm of U0 in HS smaller than epsilon, right? So this is what you might call a normalized frequency envelope. Maybe I should have said when you do this Littlewood-Paley decomposition, we don't do anything at low frequency, so everything below frequency 1 is put in a single clump. We do this only at high frequencies. All right. And so Now, once we have this frequency envelope for the initial data, we would like to say that this is inherited by the solution. And so now I'll actually be able to write down a bunch of estimates, which is what we expect the solutions to satisfy. So in particular, we would like the solutions to satisfy energy estimates. Norm of u lambda in L2 smaller than exactly the same thing that we had in there, epsilon c lambda to the power minus s. Strickard's estimates. I should really put these guys at the end, but I'm putting them here because one is more familiar perhaps with this. And these Strickard's estimates in effect come in two varieties. There's one set of Strickard's estimates for the local well-posedness problem and another set of estimates for the global well-posedness problem. So this is where the problem sort of forks. So for local well-posedness, norm of u lambda in L6. So there's a whole family of Strickard's estimates, but the only one that we actually prove, well, actually we prove them all here. Take that back, we prove them all. But I'll just write down the L6 for comparison. And also this is the only one that actually gets used in the proof, smaller than epsilon c lambda minus s. So observe that the constant here is the same as the constant here, which means that this is a Strickard's with no loss. Okay, but then for global well-posedness, it's one thing to have an estimate locally in time, it's another thing to have an estimate globally in time. And for global well-posedness, we can only prove an estimate which has a loss in it, smaller than epsilon c lambda 2/3. The important thing is the power of lambda, and this is minus 4s plus 1 divided by 6. Looks a little bit mysterious, but s is greater than 1, and we can compare what happens when s is equal to 1. There we have a 1 here, and here we have a 5/6. So in the limiting case, it's a loss of 1/6 of a derivative. All right. 3. So now I would like to put the bilinear L2 estimates. And this I will also fork in two. One when the two frequencies that interact are comparable, and the other when the frequencies that interact are not comparable. So let's call this balanced bilinear. Sorry, let me start with the unbalanced. These are easier. Bilinear L2. So this means that norm of u lambda u mu in L2 smaller than we have epsilon square, 1 from each, c lambda c mu, 1 from each, lambda to the power minus s, mu to the power minus s, and then you have a gain from the bilinear, and this is 1/2, assuming that mu is smaller than lambda. Okay, so sorry, minus 1/2. I said 1/2 and I put 1. So you sort of gain 1/2 a derivative, and this corresponds to local smoothing estimate or local energy decay. All right, and this is what happens when these two guys have separated frequency supports. But when we allow the frequency supports to come together, then we have a problem, because if I have, and let me also put a bar in here just for the purpose of this particular discussion. It doesn't matter for this estimate, obviously. But if I'm looking at the case when I'm multiplying, let's say, u lambda with u lambda bar, then I have the situation where I have the same frequency here and here. And then my bilinear estimate blows up. So I need to tame it. And the way I tame it is by putting a derivative in front. All right. So this derivative penalizes interactions which are parallel. Okay, and then this is smaller than epsilon square c lambda square lambda minus s plus 1/2. Well, and now I can put lambda minus 2s plus 1/2. So 2s for lambda and mu, and plus 1/2, this minus 1/2 from here, plus the extra derivative that we have added in here at frequency lambda. All right. So this seems sensible. And now I'm going to tweak this a little bit. What happens? If I'm looking at the Strickard's estimates, these are linear estimates, so they are invariant with respect to translations, right? Invariance with respect to translations is important. We would also need and like the bilinear estimates to be invariant with respect to translation, right? But here we have two functions, and we can translate them both in the same way, but we can also translate them separately. And so if I know this estimate for the product of these two guys, then I don't know the same estimate for the product of two translates. And so I would like to be able to translate one of this. And so how do I do this? I change the notation a little bit. I put here an x naught to signify that this function is translated by x naught. All right. So I'm multiplying one wave with a translated other wave. And this here is very sensible because we're looking at waves with different speeds. So remember my picture from last time with the red wave and the blue wave. You know, I take the blue wave, I translate it, it still has a speed that's very far away from the red wave, and things should normally work out. Okay? But then I'd like to do the same thing here. All right? And here I have a bit of a problem, because in particular, here I'm including parallel interactions, or what would be parallel interactions if I did not put the translation. But what were before parallel interactions, let me draw a picture here. So I have a blue wave, and then I have corresponding red wave. Let's say they are originally parallel, but maybe if after I translate the red, let me translate the blue wave, because green is closer to blue. I translate the blue wave is no longer parallel to the red wave in here, right? And the reason these are not parallel is because now we're looking at the variable coefficient metric, right? So the geodesics are not parallel at different points because the metric is varying. All right, so this means that I have a problem with this estimate when I have parallel interactions. And what is the fix to that? The fix to that is to penalize the estimate when x0 grows too big. All right? And so this is our ultimate balanced bilinear estimate. And so we'll have the break in just 2 minutes, but what I want, the final punchline of this story is, well, we make an assumption on the initial data. We want to prove that the solution then satisfies all of these estimates with some option here depending on whether you want to do local or global. In the case of local problem, you also want to have a similar list of estimates for the linearized problem, which I'm not going to write it down. But how do you prove all of this stuff? Well, like you do for any genuinely nonlinear PDE, you put it all inside a big Bootstrap argument. What does it mean to put it inside a big Bootstrap argument? You put a constant, a large constant everywhere in here. Okay. You assume that these estimates hold with this constant, and then you want to prove that they hold without the constant, that you can improve them. All right? And of course, one thing you have to be worried about is that you do not produce a circular argument. So making a good Bootstrap argument is easier said than done, because you have to make the right choice. But you cannot make the right choice until you get to the end and come back and see that it all works out. So if you want, this is what you see in here, is the outcome of a trial and error process to figure out exactly what is the thing that works. All right? And so what you see in here is how this frequency envelope idea allows us to refine the class of estimates that we have to prove, and then narrow down, figure out a good Bootstrap setup for the problem. Now, the Bootstrap by itself is not enough, because the Bootstrap would happen in a fixed time interval. And then if you want to get to infinity, or to whatever your local well-posedness time is, you need to do a continuity argument, right? You need to show that you can extend the time. And the way you extend the time on which Bootstrap holds is by using local well-posedness. So that's nothing fancy. So I should say here, Bootstrap plus continuity. So after the break, I will try to explain to you how we get to prove all of this estimates, at least to give you some idea. Right. So on the next board, I want to show you maybe something that should have made it onto that list if we had more foresight. How do we write the equations for the purpose of doing estimates? And of course, you could try to do the estimates with the equations written in the form we have them over there, except that if you do this, you're going to get bogged down in lots and lots of cases. So you want to have things done in some way systematically. And one good way to do that is given by Bonni's paradifferential calculus. And so the way we do this is the following. We'd like to come up with a good paradifferential flow, and then think of everything else as a source term. And then we'll fix this. What is our paradifferential flow? So we're going to disregard the terms on the right of the equation and just look at the metric terms. So now we're looking at the flow for a function v, which is localized at some frequency lambda, I dt, plus I'm writing this in a self-adjoint way, just so that it has better energy estimates. Maybe importantly, we want to allow for a source term in here. And now what is the metric that we put in here? Well, Bonni tells us that we just take the metric and we localize it to a frequency less than lambda. But unfortunately, that does not work for us. And here's why. That G is at least quadratic. And so in particular, G contains quadratic interactions which take two frequencies of size lambda, let's say, to a frequency less than lambda. But if I take two frequencies of size lambda in here, and I have another frequency of size lambda in here, that is a cubic interaction of the worst kind that could be doubly resonant. So I don't want to have it in the paradifferential equation, because that just means I'm not making a good choice for the paradifferential equation. So I'm going to use this square bracket, all right, to denote the following. This would be G of u at frequency much smaller than lambda, okay? But then I'm not happy because this guy is not necessarily localized at frequency less than lambda. So I'm going to put here a p less than lambda. All right, so this is my paradifferential version of the metric, and this is my paradifferential flow. And then we would like to write down our equation as a paradifferential equation. So the equation for u lambda, which is the lambda localization of u, would be I dt plus dxg less than lambda dx of u lambda is equal to maybe some nonlinearity. I'm going to call this n lambda of u. All right, very simple, very clean. And then in a perfect world, you might think, oh, this guy should be, in the big Bootstrap scheme, perturbative. And that is indeed the case, will indeed be the case for the local well-posedness. But it will no longer be the case for the global well-posedness result. What happens is that this n lambda contains lots of cubic and higher interactions, and in particular contains the double resonant interaction, which is the worst enemy in the global case. And we definitely don't want to put that guy in the perturbative box. So for global well-posedness, we're going to split this n lambda into two. Let's say some diagonal part, C lambda of u, u bar, and u. So a cubic part where each of these terms is at frequency lambda. And then just the rest of it I'm going to think of as perturbative. All right, so n lambda for local well-posedness I want to be perturbative. F lambda for the global well-posedness I'm going to think of as perturbative. Sorry, this is global well-posedness. So this is another place where the proof forks. And one reason this proof forks is that if you look at this C lambda term, where all of these guys are at frequency lambda, the obvious way to estimate this is by using Strickard's estimates, right? Now, if you look over there, for local well-posedness, we expect to have access to better Strickard's estimates than for global well-posedness. So for local well-posedness, we can use that Strickard's estimate to do C lambda perturbatively, but for global well-posedness, we cannot. And here's how the numerology works out somehow. In terms of, if you want local well-posedness, actually, let me not get into that. Just you can take my word for it that the C lambda can be treated perturbatively using the sharp Strickard's estimates, but not using the Strickard's estimates with losses for the global problem. All right. Now the interesting question is, how do we estimate terms we want to call perturbative? Okay, this will be of the essence, and I'll come back to that in a moment. But this is how we do the decomposition.
So just a quick question. For the local well-posedness, the threshold 1, is this given by this resonant term? Or
you could say that. You could say that, assuming that it's not conservative at least. If it's conservative, then who knows? But nobody has a result. So that's why I said generically. If you make all the wrong choices of i's and signs, then yeah. All right. So I'll come back to this board in a moment. So far I'm done with item 1 over there, and with this parenthesis, which is the paradifferential flow, and I want to go to item 2, energy estimates. And the easiest way to think about the energy estimates in density flux form is by looking at the constant coefficient problems. So maybe here you can start with the classical conservation law for the mass, okay? But instead of writing that, the fact that the mass is conserved, you want to, let me actually use, since I cannot do bold on the board, I'm going to use blue for bold. So I want to think of the mass as an integral quantity, as being some integral of a mass density. All right, and the mass density would be u square. So you're saying, you might say I'm wasting time with trivial things, yeah? And I can go even further and think of this as a bilinear form. And what is the symbol of the bilinear form? One, right? So small letter for the symbol, right? M of xi and eta is equal to 1. So now, instead of writing down the fact that this is a conserved quantity, I want to look at the time derivative of the mass. All right, and I want to, this has to be conserved, so it has to be the flux of something. It has to be the flux of what? It's going to be the flux of the momentum. Okay, what is the momentum? Let's do the imaginary part of, hopefully I get the signs right, the xu times u bar. In any case, it doesn't matter, because in these papers we really don't like to do integration by parts. So we do everything at the level of symbols. And so what we care about is the symbol of the momentum. P of xi and eta is minus xi minus eta. All right, so this is our first conservation law for the mass. And we also need the next conservation law for the momentum. So that's dt of p is equal to dx of, let's call this E. So that's at the level of the energy, where, let me just say that E of xi and eta is xi plus eta square. And if you expand this, then the density for the energy, by the way, maybe I should write this down, E of u and u bar would be something like minus dx to u times u bar minus dx to u bar times u minus dxu, hopefully I get this right, dx u bar. And so this is not exactly the energy that you're familiar with, right? And so this brings up an important point, that when you think of densities for quantities and the quantities themselves, you have to be careful what you call the density. Otherwise, your identities are not going to work out the way you'd like them to work out. And the same, in some sense, happens for the momentum. So we have to carefully choose our densities in order to have these nice identities. So this is what happens when you have the constant coefficient problem.
Why isn't there any quartic term in the energy? You don't need that.
This is for the constant coefficient linear. Right. You're anticipating a bit. I'll forgive you. All right. So now the next step would be to go to the paradifferential problem. And so that's our problem up there, okay? And now I have to make some choices. let's see. I can erase the theorems, obviously. And I'm just going to postulate that the computations for the momentum are pretty much similar to the computations for the mass. So I'm going to skip them for brevity. And so what happens if you compute the derivative of the mass for the paradifferential problem? So dt, let's say, m lambda. So here I'm looking at the, if you want, localized mass in the paradifferential problem. M lambda of u, this is the same as m of u lambda and u lambda bar. Okay, this would be equal to, and it's going to be absolutely identical, except that I'm going to also get a metric factor in here because my paradifferential operator has the metric in it. So this would be something like Vx g less than lambda, maybe, g less than lambda, p lambda of u bar, and then plus, and there would be a contribution from the source term, right? And the contribution from the source term would be v lambda, f lambda is going to be, well, twice the real part, v lambda, f lambda bar.
U and v are the same, or?
Let's imagine that u and v are the same. Which is one reason why tomorrow we're going to post an update of the paper on arXiv. All right. So this is good. This is good. What about this guy? We don't like this guy. This would like to think of the effect of the source term as being perturbative. Okay. What does it mean perturbative in here? Well, eventually we want to integrate this guy, right, in space and time. So if we integrate this in space and time, this gives us the time derivative, well, the mass between two times, right? So m lambda, that should be blue, really, between time 0 and time t, is equal to integral of this two real part v lambda f lambda, all right, without okay, dx dt. And so if I want to think about this perturbatively, then I should better hope that v lambda times f lambda belongs to L1. All right, so the notion of good source terms would be those f lambda for which v lambda times f lambda is in L1. This is a little bit a roundabout definition because it depends also on what the solution is. But still. And now I'm going to make it a little bit more complicated because eventually we'd like this to be invariant with respect to translations. So I'm going to put an x0 in here, and I'm going to ask for uniformity with respect to x0. That's because eventually this might get fed into bilinear, non-local bilinear forms. We already have the spectral projectors in here anyway, so we'd like to be more robust. And now we go back to the paradifferential flow, like I promised, and say, what do we expect of n lambda and f lambda? So perturbative terms would be something which satisfies, let's say, norm of n lambda of u times u lambda x0 bar in L1 smaller than epsilon square c lambda square lambda minus 2s, because we would be working with this in HS, let's say. So we have two HS norms. Think of this as this comes into a flux, so it has to go into a quadratic expression. So we need to gain both of our HS derivatives, the frequency envelope, and then the epsilon term. All right, and then the same will happen with this f lambda in the global term. And so then we come to a very important lemma, if we want, which says that n lambda is perturbative for local well-posedness, and f lambda is perturbative for global well-posedness. Perturbative in this sense. So this means that their contribution to the source term in the flux is integrable, right? We always want whatever is not in the density flux identity to be integrable, because then we can integrate it. All right. And I'll skip this proof. This proof is perhaps one of the longest proofs in the papers, because there are lots and lots of cases, and you want to defeat all of those cases using those sequence of estimates. The important thing, which we know from Bonny, if you want, is that when you write down the paradifferential equation, you have essentially two. The most important thing about the nonlinearity that you have left is that the two highest frequencies in the nonlinearity have to be comparable, right? And then you look at lots of cases. What happens if these two highest frequencies are very high, much larger than lambda? And then maybe they get matched against something else that's smaller. What happens if the two highest frequencies are of size lambda, which also includes the C lambda case? So you have to split this into many, many cases. And the idea is the best case scenario is you get L1 by multiplying two L2 estimates. All right? And maybe there's one case or two when you get L1 by multiplying an L2 with three L6s or something like that.
But then suppose, from what I understand, so M is cubic, so there you have an L1 estimate of a quartic term.
This is quartic, right.
Okay. So I see a gain that is quadratic on the right hand side, and so two factors, how do you?
Because some of, good question, because what is in terms of the number of derivatives, what is the worst case scenario is when you have two lambda frequencies and two frequencies much smaller than lambda. And then the two lambda frequencies will give you these two factors, but the two frequencies much smaller than lambda might give you nothing, right? So that's the best you could possibly hope for. Imagine you have two frequencies 1 and two frequencies lambda, then this is the best power you could potentially put in there.
But when in terms of epsilon then, small one?
Oh, okay. And this epsilon, actually, I should say, this is important because this comes with factors of C. You only need epsilon square. So the other epsilon square have a single purpose in life, to defeat the C. Okay? Thank you. All right. So this is what happens. This is kind of the end of the story for the density flux identities. Of course, you have to write them carefully in the case when we look at local well-posedness, except that when you look at local well-posedness, you want to write this also for the linearized equation, not only for the nonlinear equation. So now what happens when you look at the global problem? Then you have to look at the role that this guy in here plays and try to figure out what we do with it, because it's for sure not perturbative. And so what happens then is we get, again, writing this only for mass, And so imagine that I match this C lambda against a U lambda. I'm going to get maybe C lambda of U bar and U times U lambda bar, something like this. So that's a quadrilinear form. Everything is localized at frequency lambda, so that's good. But what is not quite good yet is that all the variables are the same. And this is where it's important that we work on the actual equation and not on the linearized equation, because now all the variables are the same. So what's not good about this expression? It has the same variables, but it's not symmetrized. So then we symmetrize it, which in a vague way you can think of integration by parts if you want. And you get something we call C for lambda, U bar, U bar. Another density for linear, and now this is symmetric. All right. And so now we pick a little bit at, actually this is erased, but I'll remind you anyway. We had this assumption that the cubic guy is conservative. And the fact that it's conservative tells us something about the symbol of this expression. And so and that's the fact that C lambda 4 vanishes of second order. Remember that first order vanishing condition that we had on gradient of the C of this guy at C, which is what we call the double resonant set. So when all frequencies are equal, this guy is equal to 0. That's not enough to guarantee that this quadrilinear form is equal to 0, which would correspond to a conservation law. It's only the self-interaction, 4 times self-interaction of the same wave packet that gets cancelled, not everything. All right. So now we look at this guy and we say, well, this is bad. Because if I want to estimate this quantity, I would need an L4 norm. But I don't have an L4 norm. The norm that I hope to capture globally is an L6 norm. So I could deal with the next term, possibly, which would be a term of order 6, estimated by an L6 norm, but I cannot estimate this guy by an L6 norm. So I have to get rid of it. All right? How do I get rid of it? I go down the list. I look to point 3 over there. So I'm looking at my mass and I say, oh, perhaps this mass is not good enough. I want to replace it. How do I replace the mass? How do I modify the mass? I want to replace the mass by the mass density by a better mass, m sharp, which is m plus a correction, b4, let's say lambda m. M is from the mass identity, from the mass correction of u bar, u, and u bar. All right. And so perhaps I'm hoping to get rid of C by adding a correction to mass. But of course, when I'm adding correction to mass, I implicitly have to also allow a correction to the mass flux. Okay, so then I would hope for a relation of the form dt of m sharp is dx of g less than lambda, p lambda, plus, erase this bracket, some r4 lambda m of u bar, u bar. Okay? So mass has a fourth order correction. Momentum in this formula has a fourth order correction. Plus, and I'm hoping these two fourth order corrections would get rid of this guy, the C4. If I can do this, then I'm doing a computation as if I'm working the problem with constant coefficients. But my problem is not constant coefficients, which means that I'm going to produce more errors. But these errors come from the cubic terms in the equation. So when I'm applying the time derivative to this b, the linear part is taken into account in constructing these corrections. But the nonlinear part in the equation will give sixth order terms in the expression here. So this would be plus something like R6 lambda m of u bar, u bar, u bar. And in effect, if the equation is not only cubic and higher order, also has also higher order terms, you get also terms of even better order. Okay, so easy part first. Easy, in parentheses, we'd like to estimate this in L1. You have to count derivatives, obviously, but then this is pretty clear if all the frequencies in here are equal, except that all the frequencies in here are not equal. So you have cases and cases and cases and cases and cases. Long list of cases, it all works out. You have this list of estimates to use. Littlewood-Paley, as much as you can stand, maybe 5 pages of computations, you can put this guy in L1.
Sorry, another question. When you were talking about symmetrization earlier, it was related to the fact that C lambda is like 1 plus C squared and 1 is C squared 2.
No, this has nothing to do with that. I have a function, I have a multilinear operator with 4 arguments. These 2 arguments are the same, so I want to symmetrize with respect to these 2. These 2 arguments are the same. I want to symmetrize with respect to these 2. Then I want this to be a real functional, so I can also take its complex conjugate, so I can replace this pair with this pair. So I have, if you want a group with 8 elements, right? Symmetry of this, symmetry of this, and exchanging u's and u bars. Okay. All right, so for now, I just waved my hands and said, oh, we can do these corrections. Do such corrections exist? How do you think about these corrections at the symbol level? And I'll try to squeeze this on the same board. This comes down to a symbol decomposition for this C4 lambda. So we would like to have C4 lambda is equal to, and C4 lambda should come from 2 places. One, it should come from the time derivative of B4. And time derivative of B4 means applying Laplacian here, or here, or here, or here. This means that we get delta 4. There's also a pesky I in there. Delta 4 C squared multiplied by B4 lambda. And then you have quartic contributions from the x derivative of R4. X derivative applied to frequencies xi1, xi2, xi3, xi4 gives you a factor of xi1 minus xi2 plus xi3 minus xi4. So this is plus I delta 4 psi times R4 lambda. Okay? So that would be a perfect world. So I would like to decompose a symbol as a linear combination with coefficients of these 2 symbols, delta 4 psi squared, delta 4 psi. This obviously would require that this C4 vanishes when these 2 symbols vanish. That would be the case if C lambda 4 vanishes on R. But I was telling you that C lambda 4 doesn't vanish on R, vanishes only on R2 of second order. So if you look at our papers, this is in the first paper we had slightly stronger assumptions, so that we had vanishing of C lambda on R. So we had this decomposition like this. So what happens when we only know that the C lambda vanishes on the doubly resonant set? Maybe I should say before I go there, so you can think about this like a division problem. Think maybe Malgrange preparation theorem in that direction. All right, so this has to be proved, but it's doable. So now what happens when this C lambda is only vanishing of second order on R2? Then you have to add another correction in here that also vanishes of second order on R2. And this correction looks like this, or maybe psi1 minus psi2, psi1 minus, let's see, how do I want to put this? Psi1 minus psi4 times, maybe, I don't want that, psi3 minus psi4 times, let's say, q1 lambda 4 plus psi1 minus psi4 psi3 minus psi2 times q2 lambda 4. All right, so what do we see in here? This is something that also vanishes over the 2 on the doubly resonant set, okay? And these factors in here are important because in the physical space, this amount to derivatives. Like derivative of u times u bar gives you exactly a factor of xc1 minus xc2. So we have one derivative here, another two derivatives in here. Where are these derivatives coming from? These are exactly the derivatives in the balanced bilinear estimates. Okay, so we have a balanced term in here. If I want to estimate this balanced term using balanced bilinear estimates, I should have derivatives in front. And that's exactly what I have in here. I have two derivatives, so I can write this, the contribution of this expression, essentially like a derivative of u bar times a derivative of u bar. And it's not exactly u bar, it's a bilinear form of u bar. It's not and the same here, and it's not a single expression, but it's, when you do separation of variables, it's a rapidly convergent sum. We know how to deal with that. And so, to summarize, we have this bad guy that we want to get rid of, and the fact that our problem is conservative allows us to get rid of that using three contributions. A correction to the density, a correction to the flux, and then a correction to the error term, which we can all nicely estimate. Okay, that's something, I said this very briefly, but it takes a little bit of work to do this. And now we come to interaction Morawetz. I really want to tell you a little bit about interaction Morawetz. So now I'm going to erase this board about paradifferential flow. And we want to use interaction Morawetz to okay, I did not erase the wrong board. And I'll give you an idea of how interaction Morawetz works in the constant coefficient case over there. So suppose I have two waves, u and v. And I want to look at the interaction of u and v. And then I define this interaction Morawetz functional of u and v being integral when, let's say, x is greater than y, m of u. U depends on the variable x, v depends on the variable y, so I don't have to put x and y's all the way in here. P of v minus m of v, p of u. So every u is evaluated at x, every v is evaluated at y, dx dy. And if you look at the density that corresponds to this integral in here, you see that this is just the mass density, momentum density, so you can estimate this at fixed time using bounds for mass and momentum. All right, and the important computation in here is what is the dt of this interaction Morawetz functional. All right, and so what do? You apply time derivative to each of these guys and use the density flux relations, and that turns into an x derivative, right? And then you integrate by parts, and all your integral by parts, all your integration by parts will stop at x is equal to y. So when you integrate by parts, you're left with just one variable. So you get integral, and now if you want x is equal to y, m of u, from p we get an e of v, plus m of v, e of u, minus 2p of u, p of v. All right. Classically, one would integrate by parts in here. Instead, I'm going to write down the symbols. So the symbol for this, let's say u comes with the frequencies xc1, xc2. V comes with frequencies xc3, xc4. Then the symbol here is xc3 plus xc4 square plus xc1 plus xc2 square minus 2 xc1 minus xc2 xc3 xc1 plus xc2 xc3 plus xc4. You may make a perfect square in here. So this is xc1 plus xc2 minus xc3 minus xc4 squared. It's positive, it's good. If you know Garding's inequality, that corresponds, positive symbol corresponds to a positive form, but this is not a linear operator. This is a quadrilinear form, so positive symbol is not necessarily associated with a positive form. So what do we do in here? Well, we want to integrate this, right? We want to integrate, and when we integrate, we only care about the symbol when all the frequencies add up to 0, obviously. So we look at what happens on delta 4 xc is equal to 0. And if you do the computation on delta 4 xc is equal to 0, you get that this is something like 4 times, I don't know, xi1 minus xi4 times xi2 minus xi3. And then xi1 comes from u, this comes from v bar, this comes from u bar, this comes from v. So this means that this expression in here, reinterpreted, is equal to integral of difference of an odd index minus an even index is a derivative. So this is derivative of u v bar square dx. That's your bilinear estimate. That's how interaction Morawetz works. In this very simple case, this is the simplest case. That's why this board tells you why we started with the Schrodinger equation. All right. And so far so good. And then comes work. Comes work because you would like to, first of all, do this for the paradifferential equation. When you do this for the paradifferential equation, you have the metric factors. And you might say, oh, this is easy, right? Because the metric factors are the same all over the place. But that's not true, Because suppose I want to do an estimate, suppose I want to look at I of u, let's say lambda, and u lambda, and maybe translate this guy. Then this uses the metric G, and this one uses the metric G translated. So suddenly the metric terms no longer cancel. The difference between the metric terms, you'd have to think of it perturbatively. So of course we all know fundamental theorem of calculus, but it's really a lot of work to peel off the difference of the metric and to get good estimates for the contribution of the difference of the metric embedded in all of this computation. But that's not the most important thing, not the most interesting thing. The most interesting thing is the following. Suppose now that we want to go to the global problem, and in the global problem we want to use this corrected masses and momentums, right? So for the global problem, I'm just going to put sharps in here. All right. And so now, when I do the computation, I'm going to get contributions coming from this B and contributions coming from this R in my derivative of the interaction Morawetz. So let me write this down, how it looks like. So for the global well-posedness, we compute d dt of, let's say, I sharp of u lambda u mu, if you want. So I'm applying this to two frequency localized versions of u. And maybe even the worst case scenario is when I have exactly the same frequency in here. And then what I hope to get is, let me give a name to this expression that we got in here. This was the quartic term, so I'm going to call this J4, right? Now, if instead of something quartic, if instead of something quadratic, I put something quartic, then I'll get here a contribution of order 6, right? So plus J6. Now, it's also possible that one of the B's gets multiplied by one of the R's, and that would be a J8. Maybe J10 plus, okay? Plus K, which contains the contribution of source terms. So all the pesky things we put in the perturbative box. And now the interesting question is, what happens here? Maybe let me put here u mu for now. And the most interesting case, so case 1, and also put x0 in here. Lambda is equal to mu, and x0 is equal to 0. This is the diagonal case, the balanced diagonal case. Then J4 is as before. J8, 10, and K would be perturbative. There's the integrals in here. And so the interesting bit comes from this J6. That's a 6 linear form. The 6 linear form, which you say, oh, if it's 6 linear, we can estimate it, 6 linear imbalance, let's say, we can estimate using Strickard's estimates. But then where do the Strickard's estimates come from? So we cannot estimate this using Strickard's estimates, because this J6 will be the source of our Strickard's estimates. Why is this J6 the source of the Strickard's estimates? Well, one thing we had to do, and was, at least at first sight, very computationally intensive, was to compute the symbol of J6. Yeah. And you could say, what's so bad in computing a symbol? And then I'll remind you that the way J6 is computed depends on the choice for B and R, and B and R come from this division problem. So they're not even uniquely determined. So in particular, the symbol of J6 is not even uniquely determined. But who cares? We went ahead. Who cares? We went ahead and we said, well, perhaps we don't need to know all of the symbol of J6. Perhaps we need to know enough of it. And what is enough is to compute the symbol J6 at 6 equal frequencies. Let me put a lambda in here. And what is this symbol of J6? At the end of the day, you do your computation, and you get the following. So first of all, when we localize to frequency lambda, we have the multiplier that gives us the localization at frequency lambda. And that gets used twice here and twice here. So this is, let's call that chi lambda, localization at frequency lambda of xi, taken 4 times, times c of xi and xi and c, which is exactly the guy that we assumed was real and had a sign.
And who is X4, sorry?
Hmm?
Who is the other guy in front, sorry?
This guy, chi lambda 4, this is simply localization to frequency lambda. Because I'm computing here u lambda, and no x0.
And that chi lambda q, right?
4, 2 from here and 2 from here. This is, I has in it a mass and a momentum. Each of them have 2 chi's.
I have a problem of homogeneity.
Oh, you're counting derivatives or what?
6 on the left-hand side.
Oh, it's just
No, not derivative, homogeneity. Let's,
homogeneity.
yeah. All right, so it's a bit of a leap of faith to believe this formula. In the beginning, we tried to do it by hand, to prove it by hand. We suspected this must be true. And the reason we suspected it must be true is because we knew that it's true if we checked that it was true for the cubic NLS. Okay? So what saved the day in the end is to realize that there's some Galilean invariance in here. So you don't have to compute this formula in the most general case. You can specialize it sufficiently that it becomes easy to compute. So you cheat, in other words. All right? So once you have something like this, then you say, well, I'm looking at J6. I'm taking the principal part in it. This is a positive symbol. So at the leading order, this J6 looks like an L6 norm to the power 6. So we say at the leading order, G lambda 6 x dt is integral some operator B lambda U L6 to the power 6 plus a perturbative error. Why the error is perturbative? Because the error will involve differences of frequencies, and difference of frequencies allow you to use the better bilinear L2 bound. So this is the really important thing. You do the J6 part, and this is where you use defocusing, right? This is the key part in the argument where we use defocusing. All right, and once you have this idea, everything else is just computations. Lots of computations. You have to be very careful of how you organize it, but we already have the correct bookkeeping, and so I think I hopefully gave you enough of an idea of how this process goes, except for the Strickhart's estimates that I'll tell you about in the last lecture. All right, and so I guess I'll stop here for today.
So the dispersive assumption, well, probably arises here, but it also arises in the fact that R, the resonance set, is characterized, as you said, because if you don't have this complexity at all.
Right. So that's a good point. So what I want to say, and that's why I use the omega notation, in effect, is that whenever omega is convex, you still have the same characterization of the resonance set. It does not matter the fact that omega is psi square. All that matters is that omega is convex, and that you are, of course, in one dimension. Mm-hmm.
Maybe another one. I didn't quite get what you meant when you said that J6 is the source of the Strickhart's estimates.
Because what I want to say is that the J6 term gives me an L6 norm of some localization of U plus some error terms. So maybe what I should say is this I sharp, I'm integrating this relation between two times, right? At the first beginning time and at the end time, I just estimate the mass and momentum densities, right? And that gives me information about the sum of these terms. In the sum of these terms, 8, 10, and k are perturbative, so that gives me information about J4 and J6. And I want J4 to give me a bilinear L2 contribution, and J6 to be an L6 norm, maybe plus some errors. Importantly, I want these two terms to have the same sign, right? So I'm estimating J4 plus J6 in terms of everything else. And that's how I capture my bilinear L2 estimates, and that's how I capture my L6 estimates. Here, there's more work to do, the balanced non-diagonal case and the unbalanced case. And in those cases, J6 is perturbative. So this is the single most important case when you actually use the J6 to capture the Strickhart's norm. It was a little bit quick at the end.
Okay.
But it is more of that trick, it is general or it's more for Schrödinger type equation?
That's a good question. So if you look at the last paper that we posted in October, that's where we figured out how to make it work for something that's not Schrödinger. So now we know how to do this, even if the problem is not Schrödinger, but still has a strictly convex dispersion relation.
So you have a way to see it, okay. And just a basic question. Let's say if you are focusing, so you have a difference of two terms, is there a way to relate them? Okay, so with,
if you're focusing, then we cannot make this into a global result.
Is there a way to make it to put a relation between this term and
The J4.
Who knows? In the focusing case, maybe I stated last time the other conjecture that we have a long time well-posedness instead, this epsilon to the power minus 8 threshold. And the epsilon minus 8 comes from simply not getting an L6 estimate, so we cannot get positivity here. We try to estimate this perturbatively, as in the local well-posedness results somewhat. No, we don't know how to take advantage of that in the focusing case.
Maybe another naive or more broad question. So I have the impression when you consider the wave equation, the quasi-linear wave equation, and you do these modified energies, in a way you can see it as your wave rather than traveling on the flat space. You see it as traveling on a curved space. So the modified energy is the right one you have to look at, because for Schrödinger, is there an analog of this idea, or is just like a more profound idea related to geometry, or it's just, let's say, computations?
Well, I mean, the computations, they come from, it's essentially a normal form type computation, except at each point you have to decide what is important and what is not important. You never do a computation which involves everything. You hope that there is a certain part of the equation that carries the bulk of the interaction. You do the computation based on that. And then there is a price you pay, which is extra errors, and which you have to estimate. But it's still, at heart, is the same spirit. When you talk about corrections for the wave equation, you can still put those into two boxes. One is a normal form type correction, and the other one is a quasi-linear type correction, and you'd like this to make friends.
Good. So let's try to speak again.